Other uses for X-rays and understanding came very quickly. In 1899, Hermann Haga and Cornelius Wind demonstrated X-ray diffraction through a narrow slit and estimated the wavelengths of X-rays to be about 1 times 10 to the ninth meters or 1 nanometer. That's about 1,000 times smaller than the wavelength of visible light. In 1912, Max von Laue showed X-rays diffracting through crystals. That enabled the study of the structure of materials so you could see what different element crystals looked like. Both of these indicated a wave nature for X-rays, which is what we've already spoken of. However, in 1923, Arthur Compton showed that X-rays were acting as particles when he was able to scatter low-intensity X-rays off of electrons. Now, we're going to talk about this later in a lot more detail, but much of quantum physics, which after all is the title of this chapter, focuses on the different ways of looking at light and electrons, whether they are particles or waves. More on this later. Graphs are fantastic to help you understand what's going on in an experiment or a certain phenomenon. Here's a graph of how many X-rays are produced, and we're going to put that on the y-axis. That's the intensity of the X-rays. You can't really see this, but this tells you counts per second at different wavelengths. And here's the wavelength on the x-axis. A couple things to notice here is the graph is numbered. You tell what's on the x-axis, in this case it's wavelength, and then you tell what units it's in over here. Same thing here, you have counts per second, so you can clearly understand what's going on with the graph. This type of graph is called a spectrum. And what's going on is we're varying the wavelengths of the X-rays for its specific target anode. It's made of a specific material. And this is what comes up. What do you notice about this graph? Hopefully you saw a continuous curve. And I'll go ahead and draw that out. That's this. Very smooth, well, certainly better than my line here, with two very distinct peaks. Here's one peak, and here's the other peak. The continuous part here is called Bremsstrahlung, which is German for braking rays, braking as in a car brake, something that slows you down, and results from the energy emitted by the target electrons striking the anode, the target, losing kinetic energy and releasing this energy in the form of light. The two peaks on this curve relate to the internal structure of the atoms that make up the anode. Remember, that's where the electrons are hitting, and then X-rays are being emitted from the anode. And earlier we talked about the type of X-ray does specifically depend on the anode. We're going to discuss that later in the Bohr model. So based on this, would you expect all elements to have an identical curve? In other words, when you measured the X-ray intensity due to the various wavelengths, you would get the exact same shape, this continuous Bremsstrahlung and the two peaks. Would you expect all elements to have the same curve? No, you would not. Well, hopefully you would not. Atoms of different elements are very unique, and they possess different internal structures. So these spectra can be used to identify different types of materials, like fingerprints for people. So you can see the tremendous experimental value of this, in that you could have an unknown material, you could pass it through this type of experiment, you put it as your anode, and you could actually analyze what type of material you have by using this setup. To demonstrate that point, we'll show a spectrum here of a copper anode, or an old copper X-ray tube. You can see the Bremsstrahlung. This is this fairly continuous shape here, upon which is superimposed these various peaks. You can see here's a little one, a little bigger, big. These here, when you look at this, combined with the Bremsstrahlung, you can clearly identify this as resulting from copper.